Okay, we're just gonna keep doing a couple more examples. All right. Hopefully, this is what your homework is on this week, so hopefully this is clicking a little bit. So I kind of, last time I just quickly, if you would even say in any way, went through the derivation, right? But we just, again, you could read through the text if you want to see the full derivation, but a couple key highlights that came out of it was when we talk angular momentum of an object, we look at the angular momentum of the object about its own mass center, and then we add on to it the mass center's angular momentum about some arbitrary points. You would have both of those things. It would have multiple components to it. We then took that and threw them into this equation, right? And then constrained it to the x and y direction. And when we did that, what popped out, and so if we were doing this differentially, if we're talking about the angular momentum about the mass center, so you do this differentially, and then you sum it up over the height of the thing, and you constrain it to the x and the y direction. What popped out of it was the angular momentum of an object around its own mass center is this integral of r squared dm times omega. This r squared dm we identified as being that mass moment of inertia, and so that mass moment of inertia popped out, and so the angular momentum of an object about its own mass center is its moment of inertia about that mass center times omega. So that's very analogous to linear momentum is mass times velocity. Angular momentum is I times omega, which is just another type of velocity, right? And so then we also said, oh, by the way, if you want the angular momentum about an arbitrary point, we could figure out what the I is about that arbitrary point, and then angular momentum will just be that I times omega. Then we went through, did a lot of hand waving through this, and we ended up with these three equations. So if I'm looking about the summing the moments, because again, we're trying to get a relationship between moments and accelerations. So we got down here, and we have summing the moments is equal to the derivative of hg, right, plus rg is seen from O crossed with mag. So this is really analogous to just r cross f, right? Look at what an actual moment is. But instead of r cross f, it's r cross mag. Okay, so this is the most general form of this equation that we can get. That isn't even constraining it to 2D. When we constrain it to 2D, then this hg dot component just becomes ig times alpha. Right? And so our moment about some arbitrary point will be ig times alpha plus this moment which is really close to r cross f. Right? Sometimes I think there's one problem you might have to use this most general form. And that's if you don't have a fixed point, you would have to use this, right? If you're in 2D and you have a fixed point, rotation about a fixed point, you just take I about that fixed point, and then this part goes away, right? And so you just have IO times alpha. That's your moment equation when we have a fixed point. If we're going to sum our moments about a mass center, right, then that just becomes I sum my moments about the mass center and I use Ig times alpha. Where students mess up, right, is they try to use all three of these equations. You don't need all three of the equations. You just need one, okay? And it depends on the case that you're dealing with. And then the other place students mess up is the moments of inertia that you use. If you sum the moments about a point O, then you use I about that point O. If you sum the moments about point G, you use I about G. That's the big key components here, okay? These types of problems you solve just like all the other problems, okay? Just like we did for particles, and that is, right, one added step, we have to do mass properties, but then we draw a free body diagram. We do kinematics as required. Kinematics is what you just did in your previous homework. We do equations of motion, right? It's just geometry of motion is kinematics. Equations of motion, we get 3 per body. So we get some of the force in the x, some of the forces in the y, and one of the sum of the moments equation, okay? So those are 3 equations we get to use, okay? And then we solve for unknowns after we plug everything in there, right? If you skip one of these steps, if you skip kinematics, often you'll end up with too many unknowns, and you need to go back and somehow relate all of them, okay? So we did an example problem, right? First thing we did was determine the mass properties. We had to find the mass center of this object, right? Once we figured that out, then we also determined we were going to sum our moments about point A. We didn't have to. We could have summed the moments about point G, and if we did that, then we wanted IG. Either way works. You could go either direction. We went IA. It just ends up being a little bit easier algebraically to solve it when we do it that way. So then we did that. We drew our free body diagram. You just draw everything on there that could be acting on there, okay? And then this is where a little new is our kinematics, right? on these types of problems where it's like this, you need AG, right? Our equations of motion, right, are sum of the force in the x is mass times AG, sum of the force in y is mass times AGY. I need to know what AG is, and so that's what I do. I come in, I say what AG is. This is just your regular mechanics. I take a step from a point I know something about out to the point that I want to know about, right? That AG there. So I go AG is AA plus alpha crosses RG is seen from A, and then this centripetal acceleration component. This particular problem is not moving. If it was moving, there would be an omega there, but in this case, there is no movement. So that guy's 0 and that guy's 0, right? And then you just carry out that cross product, and then everything that you get in the I direction is AGX. It's AGX. Everything you get in the J direction is going to be AGY, right? And that's important to note because we need that in the equations down below. If I skipped this step, we would have too many unknowns, okay? Then we came down, and then we did sum of the forces in the X. I just look at my free body diagram, say what's acting on it. Well, I only got AX right there, right? And then I just substitute in the 0.25 alpha. And then I come in, I look at what's happening in the Y. I got AY and I got MG, right? And then I go AY minus MG is equal to MAGY. I take that AGY, put it down there, right? And then I sum my moments, right? And I sum my moments, and like I said, from the beginning, I was going to sum my moments about point A. Here's point A right there. And so we see MG is the only thing that's going to cause a moment. It's going to do, right, roll your fingers in that direction. It's going to do a positive moment. It's important to put that in there the right way. So it's going to be AMG times the moment arm, which is 0.75, is IA times alpha. And there you go. There's my 3 equations, 3 unknowns. I've highlighted the unknowns, right? And now it's just algebra, which, as I mentioned last time, is troublesome to many of you, okay? It is troublesome. So learn how to do algebra. I have a tutoring service that I'm teaching my kids how to do algebra right now. It involves yelling at them. So if you guys want to sign up, you can come sit in on my family algebra sessions, and I will probably yell at you. So, and then one, if not all of us, will leave crying. So, like I mentioned before, when I work with my kids, one of us ends up crying. It's me going, "Oh my God, what's wrong with my child?" And then it's them going, "Oh my God, why is my dad yelling at me?" Some of you may be able to trauma. It's trauma. Some of you may be able to relate. Okay, so let's do this one, right? So this is a multiple objects, right? And so the way you do this is we're just going to draw 3 different. When you have multiple objects, you have multiple free body diagrams. So we're going to do 3 different free body diagrams for this, and then we get equations of motion for every object that we have. Okay. In this case, there isn't really much to do about mass properties, right? So this is 20 kilogram is hanging there, and a 4 kilogram is, and they're going to drop like this, right? What you have always done is just said that the tension in this part is the same as the tension in this part, right? That's a very common thing. It's not true. This is not true now. I know, it blows your mind, Jermaine, doesn't it? See, the reason it's not the same, the reason it usually is the same is this is a massless pulley up here. If it's a massless pulley, this problem becomes really easy because there's no force required to get this thing to start rotating. Now though, this thing has mass and it has a distributed mass, and we have to deal with that. And so in this case, we're going to find that the tension in this part is not the same as the tension in this part. And the difference is what's getting this thing to turn, because there has to be some torque in there to get it to turn. So just a little foreshadowing. So in this one, don't make that assumption right from the beginning. We can't do that. Okay, so mass properties is step 1. Not much mass properties to talk about here. They tell us what this is, they tell us what this is. We don't have to calculate the center of mass anywhere, and they tell us what the I is of this disk about its mass center. Right? They tell us that. So no, we got to skip step 0. We don't need anything for that. First step, though, after that is a free body diagram. F, B, D. Okay, 1 second. Hold on. It just reminded me of something. Oh. Hold on, find something. Oh yeah. If I show, maybe I've showed you this already. If I showed you this. That's us. That was real footage of me and my kids doing math homework. They would say that that's true. I think this is a good way. This reminds me of you guys studying sometimes late, studying late for something.
Hello, darkness, my old friend. I've come to talk with you again.
Some of you might try it. Right? Just get it in there. Okay, back here. All right, free body diagram. We get one free body diagram per object. Okay, so just circle. We'll do the disc first. Oh, my God. I've helped drawing circles and I still can't draw a circle. Nailed it. Okay, so we're going to do a disc. We'll do the disc first, right? So what do we have acting on this disc? Yeah, we have mass times gravity, right? That's going that way. You write everything down, right? What else do I got? That disc is just sitting there, right? Right? So I got a reaction there. Right? We'll call this, let's label this point. Let's label the point in the middle here, C. So we'll call that CY, and then we'll have a CX. Right? What else do we got? Right? Just look at the object and be like, what's pulling on this thing? Right? We got this guy out here and this guy out here. Right? Both of those guys. So, right? We'll call that TA, and then we'll call this side over here TB. Right? And we are not going to say that they're the same. We don't know. That they would turn out the same if they were the same, but we're going to keep them as separate at this point. Right? That should be everything that's acting on there. Right? Maybe one thing, we always talk about putting dimensions on here. We'll put our dimension here. The center there. They tell us that is 125 millimeters, so 0.125 meters. Now here you got to be careful, right? Since it's a kinetics problem, you got to make sure that everything goes in meters and newtons. Right, so everything turns out all right. Okay, so that's one object. That's the disc. Then we'll do A over here. A. And I say, well, what's acting on A? Well, we got gravity acting on A. Mass A times gravity, and this one is going to have TA pulling up on it. Those will be the same, right? So I'm pulling down or pulling up, or pulling down and pulling up, I guess is what I do. And so they're equal and opposite there. And then we'll do B. And a bigger mass. B. And we got MB times gravity. And then this one I got TB. Okay, there's our free body diagram. All right, you have to draw one per object in this case. Could I put it all in one? Yeah, I don't know, it gets weird. I guess you need one each. Okay? That's the first step. Okay, so now when we get to the point where we're summing forces and moments and stuff, I just look up at this and be like, oh yeah, everything's there. A nice, complete, easy to read, clear free body diagram. All right, second step, kinematics. Kinematics here is a little different. It's just geometry of motion. We'll do a step from one place to another place. And again, if you skip the kinematic step, you'll just have way too many unknowns and you have to relate them at some point. So I like to get it out of the way first. So one thing we can relate is how A is moving to B. How is A moving relative to B? Right. If B goes down, A goes up, right? If A goes down, B goes up, right? So and they should be the same velocities and the same displacements, right? Because if that cable is inextensible, which we're going to make an assumption that it is, right? Then the acceleration of A is equal to the acceleration of B minus, right? The negative of the acceleration of B, right? So that'll be one of the steps. Or one of the things that's worth pointing out. Acceleration of B is equal to the negative acceleration of A, or vice versa, right? Oh, I want to flip that. That's okay. I'll do it over here. I'll say also A is equal to the negative AB. And the reason I want to do that is that I want to be able to say something. I'm going to add a new point right here. We'll call that P. Right? Because, obviously we have the acceleration of A and the acceleration of B. And if I had a point P over here, how would the velocity or the acceleration of P relate to the acceleration at A? Acceleration here relate to the acceleration here. They're the same, right? They're the same. If there's no slip, right? If I assume there's no slip around that corner, then and this is inextensible, the acceleration of this point right here will be the same as the acceleration of this point. Right? Everybody get that? Everybody okay with that? So they will say that. That's equal to the acceleration of P. Right? This is all geometry just related to it right now. Okay? But at some point I need to get an alpha out of this, right? So let's get an alpha. And how does this relate to alpha? Because this thing is going to be turning, right? This thing is going to be turning like this, right? Should be accelerating in that direction. And so I need to get that. And so I need to somehow relate the acceleration at point P and the acceleration at point A, which are the same. I need to relate that to some alpha in this direction, right? So you could just say, well, that's a tangential acceleration, so that's just going to be R times alpha, which is correct. That is correct. If you notice that and you're okay with that, you could do that. Or, right, if you're not sure about it, then we're just going to go back to our kinematic equation and be able to say, well, I know the acceleration at this point, right? And I can take a step from here out to here, right? And then I can do it that way, right? And that's, if you're a little unclear and you don't just see that it's R times alpha, then absolutely do that, okay? And so let's do that. So we'll say AP, get your signs right and everything. AP is equal to, AC plus alpha crossed with RP is seen from C minus omega squared RP is seen from C. Okay. The problem statement says that this thing is starting out at rest, so that omega goes to 0. Okay, AC is 0. Okay, and then we just plug in our values here. Alpha in the K direction. Not that. Alpha in the K direction. I'm going to cross that with negative 0.125 in the I direction. Right? Because I want this vector here stepping over to the left there. So that's negative 0.125. And then again, we always just assume that alpha is in the positive direction. If it turns out negative, then it's negative. Okay? And so, if you carry that out, we get negative 0.125 alpha in the J direction. This would be A. So this is in the J. So this is AA, AY. Because it's equal to AA, right? AA. That's what we were just solving for. AP is equal to AA, right? And so then that's what that is. We're going to need that later, right? That's how it relates. That's just R times alpha. So if this thing rotates with the positive alpha, then that point P will go down with R times alpha. Okay? Then we go over here. And then we can also say, let's relate it to AB as well. This is ABY then is equal to 0.125 alpha. I'm going to need these later. I'm going to highlight them here. Right? AB is just going to be the negative what AA is. So I just need those for later. Are you with me? Everybody okay? Are you okay? It's just, do more people sit on this side because I talk to this side more? Is that what it is? And so you guys... It's just better? Yeah. You guys jealous a little bit on this side? Maybe I'll start talking to this side. But see, every time I look at this side, you're yawning. I just every freaking. It's almost a trigger. I look over there, and it's like I can make you yawn by looking at you. It's her fault that I'm not lecturing to this side because I lecture over here, and there's just big old yawns. Although Mark last time kind of hurt this side. You hurt last time because you were falling asleep on me. You're just testing it. See how much dedication I had. Okay. All right, so we need all those things. So we got that. So we have a relationship between AB, AA, and alpha. That's what we were after, right? And so just write them all down. You might need them later. All right, so 3 is equations of motion. Equations of motion, right? We get 3 per body, right? That's how these equations of motion work. You get 3 per body. We got 3 bodies, so we could technically have 9 of them, but we don't need some of them, right? Like these guys, I don't need the moments and I don't need the x's. There's nothing happening in those directions, so I don't need moments and x's, but I do need some of the forces in the y direction. But we'll get to that. We'll start out with the disk. I'll do the disk first, right? The disk, we do need all 3. Right? So we got some of the forces in the x direction is equal to MAGX. Right? So if we look at the forces that are acting there, we just look up at our free body diagram, and there's just one force acting in the x direction, that's CX. Right? And then its center of mass is just the middle right here, so that's not moving, right? So it's a fixed point, so the acceleration in that direction is 0. So this would just be M. Oh, did I call what that mass? Did they tell us that mass? I don't think they tell us that, but yeah, anyways. We'll call that mass of the C. We'll call it mass of the C times 0. Right? So that tells us that CX is equal to 0. Great. There is no forces acting in the x direction. Okay? Then we come down, some of the forces in the y is equal to MAGY. So we just look at our free body diagram. Right? We've got TA going down, CY going up, TB going down. So, and mass times gravity, and a mass times gravity. So we get, I didn't give myself enough room. T minus TA minus TB minus MG plus CY. And again, it's not moving, MC times 0. Okay, so this is just a statics problem, this part of it is. Okay? Because it's not moving in that direction, right? But I just write it all down. Yeah, obviously, I can't solve it at this point, right? Because you look at, I got way too, right? I got this is unknown, this is unknown, this is unknown, right? So that's as far as we can go at this point, okay? That's some of the forces in the y. Now, our one last equation we get for this body is a moment equation. I'm going to do it about the mass center because they tell us what I is about the mass center, and it turns out that the mass center is also a fixed point, both of those. So, sum of the moments about point C is equal to I about C times alpha. That's our last equation. Okay? So then I just look at sum of my moments. I've got this guy times that distance, right? That's going to be a positive moment. So TA times 0.125 is a positive. TA times 0.125, that's a positive moment, right? And then TB is going to cause a moment, and then TB is going to be a negative, right? Because it's acting down like this, right? And so it's giving us a negative moment. So this would be minus TB times 0.125. That's it, right? The other these forces right here act through it, so it has 0 moment arm. And so then that is equal to IC times alpha. They tell us what IC is, right there. I is 0.015. So this would be 0.05 alpha. There's another equation. Okay, can we solve it now? I don't think we can, right? Because we still have unknown, 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 unknown. Right? So we have four unknowns and 2 equations that use those. So we gotta keep going, right? So then we have 2 more, right? We have the sum of the forces we have the equations of motion for this guy and this guy. So let's keep going. There we go. Now we'll do this for A. Right? Again, there's only one thing happening in A, right? What's happening in the Y direction. There is no moments acting on it. There's no forces in the X direction, so we don't need to look at those directions. You could, right? You could put them in there and just see that the moments are 0, so then there'd be no alpha, and then you'd figure out that there is no forces in the X direction, so then there's no acceleration in the X direction. You could do it. There's nothing wrong with that. But we're going to do some of the forces in the Y. That's where everything's happening. MA, AY. Well, we should probably put this as mass A too. Right? And so we just look at this free body diagram and just say, well, we got MA times G going down, and I got TA going up. So we got TA minus MA times G is equal to MA times AAY, which is this guy right here. AAY is that, which is negative 0.125 alpha. Okay, now we look at B. All right, you see where we're headed here, right? This is the last one we need. B. And we get sum of the forces in the Y direction is equal to MB times ABY. Again, we just look up at our free body diagram. We got TB going up and MBG going down. Minus MB times G is equal to MB times, now ABY is 0.125 alpha. Okay. And there we go. Okay, now we got, just count them out here, or we just highlight them. I don't know, well, there's too many highlightings. Right. I don't know TA, I don't know TB, I don't know CY, I don't know alpha. Right. That's it. And so there's my 4 unknowns, and there's my 4 equations. Right? I have 4 unknowns, 4 equations. Right? How about that one, right? How about that one? How about the algebra involved with this one, right? It's not that bad though, right? I mean, you could do substitution, you could do whatever. You could, I think a TI did not do 4 equations and 4 unknowns. That's how I would do it. Beep, beep, boop, 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 boop. Beep, beep, boop. I would really like my calculator to actually make that noise. But in fact, actually, and I guess the other point is, this is what you would need if it asked for the reaction. It didn't ask for the reaction. It actually just asked for, what did it ask for? What is the tension in the rope between the 20 kilogram and the pulley? So it just asked for one of the tensions. And so you actually could get away with just these three. And those three is the TA, the TB, and the alpha. And then you don't, if you wanted the reaction, you would have to include that equation up there if you wanted CY. But I just did these three equations and these three unknowns. And what I get for the answer here is alpha is equal to negative 46.2 rads per second squared. TA is equal to 62.34 newtons. And TB is equal to 80.8 newtons. Right? So we just kind of real quickly look up and see if that makes sense. Right? The alpha ends up being a negative, right? Does that make sense? Right? It does, right? Because the thing is gonna, right? At least my intuition would say that 20 kilogram mass is gonna pull more than the 4 kilogram mass going up, and so it's gonna cause it to rotate that way, right? Which gives us a negative alpha, right? Rotate with a negative alpha. And then I told you that these aren't gonna be the same going around, right? The tension in A and the tension in B. Tension in B is bigger, I would buy that, right? And then the tension in A. And so you're like, well, where did it go, right? If it's going, right, it's going around that corner, why is there a difference? Well, the difference is because something had to make this turn, right? Something has to be applying that. Some of that force, the difference between here and here, that force is going into this pulley to get it to move, right? To get it to accelerate. Right? And that's why they end up not being the same. If you assume, like usually when you do pulley problems, you assume that this is massless, that has a zero I. If it has a zero I, it takes no force at all to get it moving. And so that's why that tension is constant as it goes around. But when it actually has mass, right, it has resistance. That mass in the middle has resistance to rotation. It won't want to rotate. And so you have to apply a moment to it to get it to rotate. Okay? Cool. Everybody all right with this one? This is a more complicated one because we had so many things going on. But literally, though, just stick to the plan. Free body diagram, kinematics as required. You're after, some sort of acceleration and how it relates to alpha because you have to make that relationship. If I don't make that relationship, I have too many unknowns, right? If I did that, this would be AAY and this would be, this would be AAY and this would be ABY, and be like, God, that's too many unknowns. You wouldn't have enough things to solve it. So you have to add kinematics and relate the accelerations to alphas, right? And then you draw your equations of motion. You pull stuff directly off your free body diagram, and then usually you get down. As you can see, the very target in a lot of these problems is you get it down to a certain number of knowns and a certain number of equations, and then it just becomes algebra, right? It's just algebra at that point. No questions? Any questions?
What about solving for the height after 0.5 seconds?
Oh, that part. Right. Once you get a great question. I actually do it here. So yeah, you're right. The problem said, what is the height of it? So then this comes back to stuff you don't like to do. Okay. And this goes in, if I know the acceleration, right? AB just ends up being equal to 0.125 alpha. That ends up being equal to negative 5.77 meters per second squared, right? Once I figure out what alpha is, which I just did, I solved for that alpha, I can then take that and put it back into this, right? This ABY. And so that gives me my acceleration in the Y direction of being negative 5.77 meters per second squared, right? And then that is a constant acceleration. And so then you could just do the height equation. Who asked that? Oh, he's right. Oh, yeah. So then you could just use your height equation for constant acceleration, right? Or your displacement equation. Y is equal to 1/2 AT squared plus V naught times T plus S naught. And then it says T is equal to 0.5 seconds, right? That's what the problem statement says. Right? And then you plug this, right? Starting out at rest, so that guy's 0, starting out at 0 displacement, or 0 position. And then this just goes, beep, right? And so it just goes back to our kinematics for 1D motion. That's what we get for that. That was a good question. You're right. I skipped that part. The hard part is this part. Coming up with what these things are. And then after that, you just go to 1D kinematics. Cool. Great question. All right, let's do this one. Or at least start this one. We won't finish this one. Oh, yeah.
For that previous question, what would you use for mass and disk?
It doesn't play in. It doesn't play in. Right? They don't give it to us. You're right. I think you could get it if they give you I and they give you the radius. You could then back calculate what the mass needed to be. You'd have to you'd have to make assumptions on what shape this was. Like if you said it's a disk, then we have the equation for calculating I based off of that disk. But in this particular one, you're exactly right. They didn't give us, but then you can see that it's, right, it doesn't play in at all. Yep. Good question though. But you could, there is an equation, I think it's 1/2 mr squared or something like that is what the moment of inertia is of a disk, and they give us the radius, and so you could back calculate what the mass was if you needed to. Good question. All right, so there's this log, okay? And then it is in a position like this, right? And then we're gonna yank on the bottom of this thing, right? And so they're showing it in one case that it could fail. So it could fail by slipping out, right? This thing could slide to the side and do that. It could also, and we don't know, tip over like that, right? Depending on how much friction force was there and how much torque it is, it could actually cause this thing to tip over as opposed to slip out underneath it. And that's why they give you mu static and mu kinetic, right? If it's slipping, it would be mu kinetic, right? If it's going to be the tip over case, it's mu static, okay? And so the way we would do this problem, or the way we're going to do this problem, is we're going to just do it in cases. We're going to look at a case, and what happens if this thing tips over, and will that work or not? And we're going to find out that it won't work, okay? And then we'll look at the case of if it's slipping out from underneath it, okay? So that's it. And then what they're after is the pole's angular acceleration at the instant the 400 Newton horizontal force is applied, okay? So at that exact instant that it is applied. So let's do case 1. Just kind of as an exercise. Case 1, right? There's gonna be a tip over. Okay? Tipping over. So what I mean by that, right? Just this thing is gonna go boop, and then it's gonna go boop, tip over. Like that. Okay? Free body diagram. FBD. We'll do the mass properties on the fly. There's only just one mass property that we need is I. Okay, so free body diagram, draw our object. And my object. Force is acting on it. I got mass times gravity. Mass times gravity. I've got a normal force acting up. I'm going to have friction resisting that. I'm going to have a 400 Newton force. 400 Newton force applied at 0.5. And that should be everything. All the forces that are acting on this thing, okay? But we should put some dimensions, because again, it's nice just to have them there. distance to the mass center. This thing is 3 meters long, I think is what it is. Yep, 3 meters long. So the mass center would be 1.5, and then they tell us this distance there as being 0.5, I believe, right? 0.5. There's my free body diagram. Okay. I'm gonna jump over here. I'm gonna do my kinematics over here. Okay, kinematics over here. Again, with these types of problems, I always think about just stepping to AG, right? So let's step to AG. Right, so I want to, and G again is the mass center, right? And so if this thing's tipping over and I'm going to G, right? If it's tipping over, do I know accelerations at any of the points? Right here, right? That if it's tipping over, the acceleration at that point is 0, right? If it's sliding, that's not the same. So that's one of the big key differences is what our kinematics are going to be based on these two different cases. So in this case, we're going to say that AA is 0. So we're going to go to AG from AA. AG is equal to AA plus alpha crossed with RG seen from A minus omega squared RG seen from A. Right? A lot of these problems, they start at rest. If they're starting at rest, there's no accelerate or no velocity there. And then AA is 0. Right? So my AG is equal to alpha in the K, always just assume positive, crossed with 1.5 in the J. Right? Because I'm just going from here to here. 1.5 in the J. And you do it at you do it in the instant that's shown. All right, at this exact instant, right? And so when you do those dimensions, sure, after a little while, the AG is going to be off to the right a little bit, but you do it just at that exact instant. So AG is just alpha in the K, crosses 1.5 in the J, and so then this ends up being equal to negative 1.5 alpha in the I direction. Right? And this is AGX. Right? AGX. AGY would be 0. Okay? So now we do equations of motion. EOMs. Okay. You got some of the forces in the X. Ooh. And X is equal to MAGX. You just look at our free body diagram and say, what is acting in the X direction? Well, I got a 400 and a friction force going back like that, just those two. Okay, this would be 400 minus the friction force is equal to M times negative 1.5 alpha, right? So I just substitute in which AGX is. Okay. And what you're going to be tempted to do, you're going to be very tempted to do this right here, is to throw in this friction force is mu times N. Right? You're very tempted to do that. But that only works if it's sliding. If it's not sliding, we don't know what that is. Okay? And a perfect example of that is this. If I just took a block, you maybe remember this from statics. I think at some point you guys talked about it. We got a block like this, just sitting on the ground, right? And I pull on it with force P, right? And if it's not moving, right? What is the force the friction force coming back this direction? And we don't know, right? You don't know. You want to say, I know you've done this a lot, that it's normal times mu, right? Normal force times mu. But the reason you can't do that here is what happens if that normal force times mu is bigger than the load that you're applying to it? It easily could be, right? It easily could be. right? So if I just pull, imagine this being like 10 newtons back this way, normal force times that is 10 newtons. But what if I only apply 1 newton? Well, then you would pull on it this way and it would accelerate away from you, right? Right? Which obviously can't happen, right? So I can't pull on it and then the force is bigger that way. So this is only, it's just P, right? It's P this way and it's P that way, right? Until it starts sliding. Once it starts sliding, then it's going to be mu static times n. Also, I know where it's going to start sliding. It's going to start sliding when this ends up being mu static times the normal force. That's the point where it will start sliding. So what we're going to do is we're going to go through and figure out what this F is and compare it to what it would be to make it slide, right? And what we should find is that it ends up being bigger than what it takes to make it slide, which means that it's going to slide. Okay. So, but anyways, right now, that's just an unknown. We can only put it in as being the friction force. Once it's sliding, though, then it is mu static times the normal force. Okay. That's just a concept that I've witnessed in the past, students having some issues with. Some of the forces in the y direction equal to MAGY. The only thing happening in that direction, we have a normal force acting up and a mass times gravity acting down, and that is equal to 0 because there is no acceleration up and down in this, and so that just tells us that the normal force is equal to mg. Right, so here's an equation. Right, here's an equation. Okay, and then we have too many unknowns, right? I don't know what alpha is. I don't know what the friction force is, right? So I can't solve it yet. I need to keep going. The last equation I get is my moment equation, right? Some of the moments. I'm going to do it about the mass center. Right? This one has a fixed point, so I could do it about point A. The difference, though, is do they tell us? They tell us what I is about the mass center. Since they already told us that, let's just sum the moments about that mass center. So this is just going to be equal to Ig times alpha. And so I just write down my moments. I got this 400 Newton force. We're almost there. 400 Newton force is going to cause it's going to cause a positive, right? I'm doing these things I'm summing the moments about the mass center. So that 400 Newton force is going to cause a positive moment. And then that friction force is going to cause a negative moment about the mass center, right? And that's the only two forces that would cause a moment here. So this would be 400 times 1 is the moment arm there, minus the friction force times 1.5. The moment of the friction force, or the moment arm of the friction force is 1.5. And then that's equal to I times alpha, which is 75 alpha. Okay? And there's my additional equation that I have. Okay? So I can then solve this equation and this equation. Right? And it'll tell me what the friction force would need to be. Friction force is 300 newtons. Right? And then my alpha ends up being equal to negative 2/3 radians per second squared. Okay, that's what I get for an answer. So in order for it to tip over like this, my friction force would have to be at least 300 newtons, and then alpha would be negative, right? Which I would buy that because it's tilted that way, so it should be a negative there. Okay, so real quick, can it do this, right? And so what we'll do is we'll look at F max, the friction max. Right? That is going to be the normal force times mu static, which ends up being equal to 100 times 9.81 times 0.3. And that ends up being equal to 294 newtons, right? Right. F is greater than F max. Right? So it slips. A little more complicated one, but that's the big finding there, right? Is that in order for it to tip over like this, the friction force would have to push back with at least 300 newtons it can't do it, right? Because before it gets there, right, the maximum that the static can hold would be 294 newtons. And so this wouldn't happen, right? It would slide out from underneath it, right? So then on Friday, we'll finish this problem, right? And basically we just come back, we just take the exact same process. The only thing the difference, this stays the same, but then the only thing that's different is what this is, right? And we make a trade-off. My kinematics change, and I don't know the acceleration at point C, but I do know in this second case what the friction force is. When it's sliding, that friction force, I do know what it is, and it is the normal force times the mu kinetic friction. So, anyways, we'll finish it next time. Break.